A 7 billion-year-old traveler from the ancient depths of space just arrived at our doorstep, moving faster than any cosmic visitor we have ever seen. This is not science fiction. On July 1st, 2025, astronomers detected something that should not exist: an interstellar comet potentially 15 miles wide, racing through our solar system at 130,000 miles per hour, carrying secrets from when the universe was half its current age. Unlike the mysterious Oumuamua or comet Borisov, this visitor called 3I Atlas might be the oldest object humans have ever observed, and we have only months to unlock its mysteries before it disappears into the void forever. Please like and subscribe as we journey into the unknown. Prepare yourselves. We begin. Deep in the Chilean desert, an automated telescope captured 4 pixels of light that would rewrite astronomy textbooks forever. July 1st, 2025 started like any other night at the Asteroid Terrestrial Impact Last Alert System Observatory. The massive telescope swept the southern sky, hunting for dangerous space rocks that might threaten Earth. But astronomer Larry Deno noticed something wrong with object A11P I3Z. The movement pattern looked impossible. Most asteroids and comets follow predictable oval paths around our sun. But this object traced a path so extreme it could only mean one thing. It came from another star. Within hours, telescopes across the globe swiveled toward this cosmic intruder. The numbers that came back defied belief. The object moved so fast that our sun's gravity could never capture it. Its orbital eccentricity measured 6.2, making it 3 times more extreme than any previous interstellar visitor. To put this in perspective, imagine throwing a baseball so hard that it not only escapes Earth's gravity, but shoots clean out of our entire galaxy. The confirmation came swift and decisive. This was not a piece of solar system debris knocked loose by planetary gravity. Pre-discovery images stretched back weeks, showing the object had been approaching from the direction of the galactic center, traveling through the cold emptiness between stars for millions of years. The Minor Planet Center made it official. 3I Atlas, the third confirmed interstellar object in human history. But 3I Atlas immediately stood apart from its predecessors. Where Oumuamua measured just quarter-mile long and comet Borisov stretched less than 1 mile across, early estimates suggested this newcomer might span 15 miles in diameter. That would make it 60 times larger than Oumuamua, a size difference equivalent to comparing a basketball to a grain of sand. As dawn broke over observatories worldwide, astronomers realized they were witnessing something unprecedented. This was not just another visitor from interstellar space. This was potentially the oldest, largest, and fastest cosmic wanderer ever detected, carrying information from an era when our solar system had not yet formed. The evidence that 3I Atlas originated beyond our solar system reads like a cosmic crime scene investigation. Every object born in our solar system follows the same basic rules of orbital mechanics. Planets, asteroids, and comets all dance around the sun in elliptical paths, bound by gravity like dancers on invisible strings. But 3I Atlas shattered these rules the moment astronomers plotted its trajectory. The object followed what mathematicians call a hyperbolic orbit, meaning its path curves so sharply that it will never return. Think of it like throwing a rock at a mountain. Throw gently, and the rock falls back to Earth in an arc. Throw harder, and you might achieve orbit. But throw with the force of a cannon, and the rock escapes Earth's gravity forever, flying off into space in a straight line. 3I Atlas travels through our solar system like that cannonball, moving far too fast for our sun to ever recapture it. The velocity measurements told the complete story. When 3I Atlas first appeared in our telescopes, it was already moving at 61 kilometers per second relative to the sun. That speed exceeds the solar escape velocity by a massive margin. No gravitational encounter with Jupiter, Saturn, or any other planet could have accelerated a solar system object to such extreme velocities. Astronomers traced its path backward through computer simulations, watching the object's journey in reverse, like rewinding a movie. The calculations showed 3I Atlas approaching from interstellar space, traveling for potentially millions of years through the void between stars. Its origin point lay in the direction of the constellation Sagittarius, near the dense star fields of our galaxy's center. But the most convincing evidence came from what scientists call the velocity vector analysis. 3I Atlas moved through space with a combination of speeds that matched no population of objects native to our solar system. Instead, its motion aligned with the thick disk of ancient stars in the Milky Way, stellar populations that formed when the galaxy was young and chaotic. This cosmic visitor had wandered the galaxy for eons before stumbling into our neighborhood, carrying with it the chemical fingerprints and physical characteristics of its alien birthplace. The verdict was unanimous. 3I Atlas represented a messenger from the deep past and distant space. 3I Atlas may be older than our entire solar system, making it a time capsule from the universe's ancient history. When astronomers analyzed the trajectory and motion of 3I Atlas, they uncovered something extraordinary. The object's path through space suggested it belonged to the thick disk population of the Milky Way galaxy, a stellar neighborhood filled with some of the oldest objects in our cosmic vicinity. Computer models estimated this wandering comet formed between 7 and 14 billion years ago, making it potentially 3 times older than Earth itself. To understand how ancient this makes, 3I Atlas consider that when this object first condensed from cosmic dust and ice, our sun did not exist. The patch of space where Earth now orbits was empty void. The entire solar system was still a distant future possibility, waiting for the gravitational collapse of an interstellar gas cloud that would not occur for billions more years. This extreme age explains 3I Atlas's unusual characteristics. Unlike younger comets from our solar system's outer reaches, this visitor shows signs of prolonged exposure to cosmic radiation and interstellar weathering. Its reddish coloration hints at complex organic compounds called tholins, formed when ultraviolet light and cosmic rays bombard simple carbon molecules over geological timescales. The thick disk origin tells us even more about 3I Atlas's heritage. While our sun resides in the thin disk of the galaxy, surrounded by relatively young stars rich in heavy elements, 3I Atlas came from a population of ancient stars with much lower metal content. These elder stars formed when the Milky Way was still assembling itself, before multiple generations of stellar explosions had enriched the galaxy with the elements we see today. Matthew Hopkins at the University of Oxford calculated that 3I Atlas represents a fossil from the early universe, preserved in the deep freeze of interstellar space for longer than complex life has existed on Earth. When this comet first formed, the most advanced life forms on our planet were single-celled bacteria. Dinosaurs, mammals, and humans were unimaginably distant future developments. The implications stagger the imagination. 3I Atlas witnessed the formation and death of countless stars during its journey through space. It survived galactic collisions, stellar explosions, and cosmic catastrophes that reshaped entire star systems. Now this ancient wanderer has arrived in our solar system, offering humanity its first close look at matter from the early universe. The enormous size of 3I Atlas creates a cosmic puzzle that challenges our understanding of interstellar objects. When astronomers first measured the brightness of 3I Atlas, the numbers seemed impossible. Based on how much sunlight the object reflected, initial calculations suggested a diameter of approximately 20 kilometers, or about 12 miles across. This would make 3I Atlas roughly 60 times larger than Oumuamua and 15 times bigger than comet Borisov, the 2 previous interstellar visitors. The size problem runs deeper than simple measurements. Statistical models predict how many interstellar objects of different sizes should pass through our solar system. According to these calculations, for every 20-kilometer object, like 3I Atlas, we should detect roughly 1 million objects the size of Oumuamua. Yet, in 8 years of intensive sky surveys, astronomers have found only 3 interstellar visitors total. This statistical mismatch suggests something fundamental about 3I Atlas defies our expectations. Harvard astronomer Avi Loeb calculated that discovering such a large interstellar asteroid has a probability of just 1 in 10,000, making it virtually impossible under normal circumstances. The odds are so extreme that scientists began questioning whether 3I Atlas truly measures 20 kilometers across. 2 competing theories emerged to explain the size anomaly. The first proposes that 3I Atlas is actually a comet whose brightness comes not from a solid nucleus, but from reflected sunlight bouncing off an enormous cloud of gas and dust. In this scenario, the solid core might measure only 1 or 2 kilometers across, while the glowing coma extends tens of kilometers in all directions. The second theory suggests 3I Atlas has an unusually high albedo, meaning its surface reflects much more sunlight than typical space rocks. Certain minerals and ice compositions can create highly reflective surfaces, making small objects appear much larger and brighter than their actual size would suggest. Recent observations from the Hubble Space Telescope and ground-based observatories lean toward the comet explanation. Images show a faint, diffuse envelope surrounding 3I Atlas, consistent with gas and dust streaming away from a warming nucleus. However, the coma appears surprisingly compact and faint compared to what astronomers expected for such an active comet. The size mystery of 3I Atlas continues to challenge our understanding of how objects form and survive in interstellar space. 3I Atlas races through our solar system faster than any cosmic visitor in recorded history, carrying enough kinetic energy to reshape worlds. When 3I Atlas first appeared in telescopes, it was already traveling at 137,000 miles per hour relative to our Sun. That velocity translates to 38 miles per second, fast enough to cross the entire United States in under 3 minutes. By the time it reaches its closest approach to the Sun in October, gravitational acceleration will boost its speed to over 150,000 miles per hour. To put this incredible velocity in perspective, consider that most comets from our solar system's outer regions travel at speeds between 20 and 40,000 miles per hour when they visit the inner system. 3I Atlas moves more than 3 times faster than these familiar visitors, carrying kinetic energy equivalent to billions of nuclear weapons. The extreme speed creates both opportunities and challenges for astronomers studying the object. On one hand, the rapid motion allows 3I Atlas to traverse our solar system in just a few months, providing a compressed timeline for observations. On the other hand, the high velocity makes it virtually impossible to intercept with current spacecraft technology. Engineers at NASA and other space agencies quickly calculated whether existing rockets could launch a probe to rendezvous with 3I Atlas. The results were discouraging. Even the most powerful launch vehicles would require gravitational assists from multiple planets and decades of flight time to match the object's trajectory. By the time any spacecraft could reach the intercept point, 3I Atlas would have long since departed for interstellar space. The speed differential also complicates ground-based observations. 3I Atlas moves so quickly across the sky that telescopes must constantly adjust their pointing to track the object. Long exposure photographs, essential for gathering detailed spectroscopic data, suffer from motion blur as the comet streaks through star fields. This breakneck pace reflects 3I Atlas's interstellar origin. Objects native to our solar system move at speeds dictated by their orbital distance from the Sun, but 3I Atlas carries the velocity signature of its journey through the galaxy, moving at speeds typical of stars orbiting the galactic center rather than planets orbiting our local star. The combination of size and speed makes 3I Atlas a kinetic monster, unlike anything astronomers have previously encountered in our cosmic neighborhood. 3I Atlas escaped from one of the Milky Way's oldest and most chaotic stellar neighborhoods, carrying the scars of galactic violence. When astronomers trace the motion of 3I Atlas backward through computer simulations, They discovered its origin lay not in the familiar thin disk where our sun resides, but in the thick disk of the galaxy. This distinction matters more than it might initially seem, because the thick disk represents a completely different chapter in cosmic history. The thin disk of the Milky Way, where Earth and most nearby stars live, formed relatively recently in galactic terms. It consists of young, metal-rich stars born from gas clouds enriched by previous generations of stellar explosions. These stars orbit the galactic center in organized, nearly circular paths, creating the flat spiral structure we recognize in images of our galaxy. But the thick disk tells a different story. This stellar population formed during the galaxy's violent youth, when cosmic collisions and gravitational chaos dominated the neighborhood. Thick disk stars follow highly elliptical orbits that carry them far above and below the galactic plane, reflecting the turbulent conditions of their birth era. 3I Atlas's velocity components reveal its thick disk heritage. The object moves with a vertical velocity of 18.5 kilometers per second relative to the galactic plane, much higher than typical thin disk objects. This motion suggests 3I Atlas follows a tilted orbit around the galaxy, spending significant time in the sparsely populated regions above and below the main stellar disk. The thick disk environment explains many of 3I Atlas's unusual characteristics. Stars in this population typically have lower metallicity than their thin disk cousins, meaning they contain fewer heavy elements forged in stellar furnaces. Objects forming around these ancient stars would reflect this chemical composition, potentially explaining 3I Atlas's unusual spectral properties. The thick disk also experiences different gravitational influences than the thin disk. Passing star clusters, infalling dwarf galaxies, and spiral arm interactions create a more chaotic environment where planetary systems suffer frequent disruption. Comets and asteroids get ejected into interstellar space at much higher rates, explaining why thick disk populations might produce more wandering objects like 3I Atlas. This cosmic refugee has spent billions of years traveling between the scattered stars of the thick disk before eventually stumbling into our solar system, carrying with it the chemical and physical signatures of the galaxy's ancient past. The trajectory of 3I Atlas breaks astronomical measurement scales with an orbital eccentricity so extreme it redefines what scientists consider possible. In orbital mechanics, eccentricity measures how stretched or elongated an object's path appears. A perfect circle has an eccentricity of 0, while increasingly flattened ellipses approach an eccentricity of 1. Objects following parabolic escape trajectories reach exactly 1, and hyperbolic trajectories exceed this value. 3I Atlas shattered all previous records with an orbital eccentricity of 6.2. To understand how extreme this measurement is, consider that Oumuamua, the first confirmed interstellar object, had an eccentricity of 1.2. Comet Borisov measured 3.6. 3I Atlas exceeds both by enormous margins, making its trajectory appear almost perfectly straight rather than curved. This extreme eccentricity means 3I Atlas approaches the Sun at an incredibly steep angle before making a sharp turn and departing just as dramatically. Unlike comets from our solar system's outer regions, which arrive gradually and depart slowly, 3I Atlas appears to punch through the inner solar system like a cosmic bullet. The mathematical implications of such high eccentricity create challenges for astronomers trying to predict the object's future path. Small measurement errors in position or velocity get amplified enormously when calculating trajectories for hyperbolic orbits. Precise tracking requires constant observations and frequent orbital updates to maintain accuracy. The extreme trajectory also affects how 3I Atlas interacts with solar radiation and the solar wind. Most comets spend months slowly approaching the Sun, allowing their surfaces to warm gradually and outgas steadily. But 3I Atlas races through the temperature zones so quickly that its surface may barely have time to respond to changing solar heating. This rapid transit creates a compressed timeline for cometary activity. Instead of the months or years of tail development seen in typical comets, 3I Atlas may experience only weeks of peak outgassing around its closest solar approach. Astronomers have a narrow window to observe maximum activity before the object cools and fades again. The record-breaking eccentricity of 3I Atlas represents the most extreme gravitational trajectory ever measured for a natural object, pushing the boundaries of orbital mechanics into uncharted territory. 3I Atlas displays the faintest cometary activity ever observed for an object of its size, creating a puzzle that challenges our understanding of comet behavior. When astronomers first confirmed 3I Atlas was indeed a comet rather than an asteroid, they expected to see dramatic outgassing and a prominent coma of gas and dust. After all, early size estimates suggested this was potentially the largest comet ever discovered. Instead, observations revealed only the faintest hint of cometary activity, barely detectable even with the world's most powerful telescopes. Typical comets develop extensive comas when solar heating vaporizes surface ice, creating expanding clouds of gas and dust that can stretch hundreds of thousands of miles across. These glowing envelopes often become the most prominent feature of a comet, visible even to naked eye observers when the object approaches the inner solar system. But 3I Atlas defied these expectations. Hubble Space Telescope images showed a compact, barely visible coma extending only a few thousand miles from the nucleus. Ground-based observations detected weak spectral signatures of dust, but none of the bright emission lines that characterize active cometary outgassing. Several theories attempt to explain this anomalous behavior. The most likely explanation suggests 3I Atlas has a composition different from typical solar system comets. Billions of years in interstellar space may have altered its surface chemistry, creating a resistant crust that inhibits outgassing even under solar heating. Another possibility is that 3I Atlas formed in a stellar environment very different from our Sun's neighborhood. The low metallicity of thick disk stars might have created comets with unusual ice compositions or mineral content that respond differently to solar radiation. The faint coma might also result from the object's extreme speed. While typical comets spend months warming gradually as they approach the Sun, 3I Atlas races through temperature zones so quickly that its surface may barely have time to sublimate. The rapid motion could suppress normal cometary activity, creating only weak, transient outgassing. Some astronomers propose that 3I Atlas might be a transition object between an asteroid and comet, containing just enough volatile material to create minimal activity. This would explain both its relatively faint coma and its survival through billions of years in interstellar space. The coma mystery of 3I Atlas continues to challenge conventional models of comet behavior and composition. 3I Atlas will vanish behind the Sun during its most active period, creating a cosmic magic trick that denies astronomers their best opportunity to study this ancient visitor. The cruel irony of 3I Atlas's trajectory became apparent as astronomers calculated its future path through the inner solar system. Just as the comet reaches perihelion, its closest approach to the Sun, when surface heating should trigger maximum outgassing and spectacular tail development, the object will pass directly behind our star as viewed from Earth. This celestial alignment, called solar conjunction, will render 3I Atlas completely invisible to ground-based telescopes for several critical weeks in late October and early November 2025. During this period, when the comet should display its most dramatic activity, astronomers on Earth will be powerless to observe it. The timing could not be worse for scientific study. Perihelion represents the moment when solar radiation reaches maximum intensity on the comet's surface, potentially vaporizing subsurface ice that has remained frozen for billions of years. This is when 3I Atlas might finally reveal its true composition through spectroscopic analysis of its expanding coma and developing tail. Instead, Earth-based observers will lose sight of the object just as it enters this crucial phase. Telescopes cannot point toward the Sun without risking severe damage to sensitive instruments, creating an observation blackout that will last until 3I Atlas emerges on the other side of our star in early December. The disappearing act presents both scientific frustration and unexpected opportunity. While Earth-based telescopes will be blind, spacecraft already in space may have clear views of 3I Atlas during its hidden phase. Mars orbiters, positioned on the opposite side of the Sun from Earth, could potentially observe the comet throughout its perihelion passage. NASA and other space agencies are frantically reprogramming existing missions to capture images of 3I Atlas during its solar conjunction. The Mars Reconnaissance Orbiter, MAVEN, and other spacecraft may provide humanity's only glimpse of this ancient visitor during its most active period. The solar eclipse of 3I Atlas also creates an intriguing possibility for stealth observations. Some astronomers have proposed using spacecraft positioned at the Sun-Earth Lagrange points to maintain visual contact with the comet throughout its passage behind our star. When 3I Atlas finally emerges from solar conjunction in December, it may have transformed completely, displaying the dramatic tail and coma that remained hidden during its closest solar approach. The discovery of 3I Atlas triggered the largest coordinated observation campaign in astronomical history, as every major telescope on Earth and in space turned toward this fleeting visitor. Within hours of the initial detection announcement, observatories across the globe began an unprecedented mobilization. The Hubble Space Telescope immediately adjusted its schedule, pointing its precise instruments toward 3I Atlas for detailed imaging and spectroscopy. The James Webb Space Telescope, humanity's most powerful space observatory, prepared to study the object's infrared signature and search for chemical fingerprints invisible to other instruments. Ground-based facilities joined the campaign with equal urgency. The Gemini North Telescope in Hawaii captured some of the first detailed images, showing 3I Atlas's compact coma. The Very Large Telescope in Chile began spectroscopic observations to determine the object's composition. Amateur astronomers worldwide contributed observations through distributed networks, creating a global surveillance system tracking the visitor's every movement. The coordination effort faced unique challenges due to 3I Atlas's rapid motion across the sky. Unlike stationary astronomical targets that remain in fixed positions for years, this interstellar visitor races through different constellations weekly, requiring constant updates to telescope pointing and scheduling systems. Observatory directors made difficult decisions about which routine observations to cancel or postpone. The scientific value of studying an interstellar object outweighed almost any other research priority, leading to an extraordinary reallocation of telescope time worth millions of dollars. Radio telescopes joined the effort, searching for any emissions that might reveal unexpected characteristics of 3I Atlas. The Very Large Array in New Mexico and the Arecibo successor facilities scanned for signals across multiple frequencies, hoping to detect plasma interactions or unusual electromagnetic signatures. Space agencies coordinated observations from multiple spacecraft, creating a three-dimensional view of 3I Atlas from different vantage points throughout the solar system. This multi-platform approach promised to reveal details impossible to discern from Earth-based observations alone. The observation campaign represented more than just scientific curiosity. With only months to study 3I Atlas before it departs for interstellar space forever, astronomers understood they were witnessing a once-in-a-lifetime opportunity to examine matter from the ancient universe. The preliminary results began streaming in within days, each observation adding new pieces to the puzzle of this mysterious cosmic wanderer. When humanity's most famous space telescope turned its precision instruments toward 3I Atlas, the images revealed details that deepened the mystery rather than solving it. The Hubble Space Telescope had observed thousands of comets during its 3 decades in orbit, but nothing prepared astronomers for what they saw when Hubble's cameras focused on this interstellar visitor. The images showed a surprisingly compact object surrounded by what appeared to be a faint, asymmetric envelope of material. Unlike the dramatic, flowing tails of typical comets, 3I Atlas displayed only subtle hints of activity. The high-resolution imagery revealed textures and features invisible to ground-based telescopes. Hubble's instruments detected a slight elongation in the object's appearance, suggesting either an irregular shape or a very faint tail aligned with its direction of motion. The envelope of material around 3I Atlas measured only a few thousand miles across, remarkably small for what might be the largest comet ever discovered. Most puzzling was the envelope's behavior. Traditional comets develop comas that expand symmetrically as solar heating vaporizes surface ice. But 3I Atlas showed an irregular pattern of brightness that changed over the course of Hubble's observations. Some regions appeared slightly brighter, while others remained dim, creating an asymmetric glow that defied standard comet models. The Space Telescope's spectroscopic instruments searched for the chemical signatures that characterize active comets. They found traces of dust particles reflecting sunlight, confirming that 3I Atlas was indeed shedding material into space. However, the spectral lines remained frustratingly weak, providing only hints about the object's composition rather than definitive answers. Hubble's infrared capabilities revealed another surprise. 3I Atlas appeared warmer than expected for an object at its distance from the Sun, suggesting either unusual surface properties or internal heat generation. This thermal anomaly added another layer to the growing list of characteristics that set this visitor apart from familiar solar system objects. The telescope's precise tracking also allowed astronomers to measure 3I Atlas's rotation period and orientation. Preliminary results suggested the object tumbled through space with a complex rotation pattern, possibly indicating an irregular shape or internal structure different from typical comets. Perhaps most significantly, Hubble's observations confirmed that 3I Atlas was gradually brightening as it approached the Sun, but not at the rate predicted by standard comet models. The brightening curve appeared flatter than expected, suggesting the object's surface responded differently to solar heating than conventional cometary materials. These Hubble revelations transformed 3I Atlas from a simple interstellar comet into something far more enigmatic, an object that challenged fundamental assumptions about how ancient comets should behave. The mysterious reddish coloration of 3I Atlas tells a story of billions of years spent wandering through the radiation-soaked emptiness between stars. When astronomers analyzed the reflected sunlight from 3I Atlas, they discovered the object's surface appeared distinctly reddish compared to typical solar system comets. This coloration was not dramatic like the rust-red surface of Mars, but rather a subtle tint that became apparent only through careful spectroscopic analysis. The reddening pattern provided crucial clues about the object's ancient history and composition. The red coloration most likely results from complex organic compounds, called tholins, formed when cosmic radiation and ultraviolet light interact with simple carbon-based molecules over geological timescales. Think of tholins as cosmic rust, but instead of iron oxidizing in air, carbon compounds slowly transform under the relentless bombardment of high-energy particles in interstellar space. This process requires immense amounts of time to produce noticeable effects. Objects in our solar system, protected by the Sun's magnetic field and surrounded by relatively dense solar wind, experience much lower radiation levels than those wandering through interstellar space. The pronounced reddening of 3I Atlas suggests prolonged exposure to the harsh environment between stars, supporting estimates that this object spent billions of years in cosmic exile. The tholin formation process also explains some of 3I Atlas's other unusual characteristics. These organic compounds create tough, resistant surface crusts that could inhibit normal cometary outgassing. While typical comets develop active regions where subsurface ice vaporizes and escapes easily, tholin-crusted surfaces might suppress such activity, explaining the remarkably faint coma surrounding this massive object. Laboratory experiments with tholin formation show these compounds can create surfaces with unusual reflective properties. Depending on their exact composition and structure, tholins can appear either very dark and absorbing or surprisingly bright and reflective. This variability might explain why early brightness measurements of 3I Atlas yielded confusing size estimates. The red surface also provides insights into the object's internal structure. If 3I Atlas formed in the outer regions of an ancient planetary system, it would originally have consisted primarily of water ice mixed with dust and simple organic compounds. Billions of years of cosmic ray exposure would have converted the surface layers into complex tholins while leaving the interior relatively unchanged. This creates a layered structure with a processed, radiation-altered exterior surrounding a pristine, ancient core. As 3I Atlas approaches the Sun and begins to warm, the outer tholin layer might crack or sublimate, potentially exposing the unaltered materials beneath and revealing the original composition of this ancient wanderer. The red enigma of 3I Atlas serves as a cosmic clock, recording the passage of time through the slow transformation of its surface chemistry. 3I Atlas shatters every pattern established by previous interstellar visitors, proving that cosmic wanderers follow no predictable rules. When Oumuamua first appeared in 2017, astronomers thought they understood what interstellar objects should look like. This cigar-shaped visitor displayed no cometary activity, tumbled rapidly through space, and measured only a few hundred yards long. It seemed to represent a new class of cosmic debris, interstellar asteroids ejected from alien planetary systems. 2 years later, Comet Borisov completely overturned these expectations. Unlike Oumuamua's mysterious behavior, Borisov acted exactly like a familiar solar system comet. It developed a prominent coma and tail, responded predictably to solar heating, and showed clear signs of water vapor and other typical cometary gases. Astronomers breathed a sigh of relief, thinking they had encountered a normal comet that simply happened to originate elsewhere. 3I Atlas destroyed both patterns with characteristics that fit neither category. Its enormous size dwarfs both previous visitors, potentially measuring 15 times larger than Borisov and 60 times bigger than Oumuamua. Yet despite this massive scale, it displays weaker cometary activity than much smaller objects, showing only hints of the dramatic outgassing that should characterize such a large comet. The speed differences are equally dramatic. Oumuamua moved at about 26 kilometers per second relative to the Sun, while Borisov traveled at 32 kilometers per second. 3I Atlas races through our system at 68 kilometers per second, more than twice as fast as either predecessor. This extreme velocity suggests a completely different origin and ejection mechanism. The orbital characteristics tell different stories for each visitor. Oumuamua followed a moderately hyperbolic trajectory with an eccentricity of 1.2. Borisov's path showed an eccentricity of 3.4. 3I Atlas breaks all records with an eccentricity of 6.2, following the most extreme trajectory ever measured for a natural object. Even their approach directions differ dramatically. Oumuamua arrived from the direction of the constellation Lyra, appearing to come from the thin disk of relatively young stars. Borisov approached from Perseus, suggesting origin in a different stellar population. 3I Atlas comes from Sagittarius, near the galactic center, indicating birth in the ancient thick disk population. The age estimates compound the confusion. Oumuamua appears relatively young in galactic terms, perhaps 1 to 2 billion years old. Borisov shows intermediate age characteristics. 3I Atlas may be the oldest of all, potentially predating our solar system by billions of years. These three visitors represent completely different types of interstellar objects, each with unique characteristics that challenge astronomical theories. Rather than revealing a consistent pattern of cosmic wanderers, they demonstrate the incredible diversity of objects drifting through our galaxy. The comparison chaos suggests astronomers have barely begun to catalog the variety of interstellar visitors that might exist. A controversial group of scientists has proposed that 3I Atlas might be artificial technology from an advanced extraterrestrial civilization, sparking fierce debate in the astronomical community. Harvard astronomer Avi Loeb, who previously suggested Oumuamua could be alien technology, has co-authored a provocative new paper questioning whether 3I Atlas represents natural phenomena or something far more extraordinary. The paper, written with colleagues from the Initiative for Interstellar Studies, presents a series of observations that they argue are difficult to explain through conventional astrophysics. The alien technology hypothesis rests on several unusual characteristics of 3I Atlas. First, its trajectory brings it surprisingly close to 3 planets: Venus, Mars, and Jupiter. The probability of such planetary encounters occurring by chance measures less than 0.05%, suggesting either remarkable coincidence or deliberate design. Second, the object's arrival timing raises intriguing questions. Tracing its path backward through space, 3I Atlas would have entered the outer boundaries of our solar system approximately 8,000 years ago, roughly coinciding with the development of advanced human civilization and written history on Earth. The researchers note this correlation without drawing explicit conclusions, but the implication remains provocative. Third, 3I Atlas will be hidden behind the Sun during its closest approach, potentially allowing a hypothetical spacecraft to perform what engineers call a reverse solar Oberth maneuver. This advanced technique would use the Sun's gravity and a precisely timed rocket burn to dramatically alter the object's trajectory, possibly allowing it to remain bound within our solar system rather than departing for interstellar space. The controversial paper also highlights 3I Atlas's lack of clear spectroscopic signatures indicating cometary outgassing. Despite appearing as an active comet in images, detailed analysis has failed to detect the specific chemical emissions that characterize natural comets. This absence of expected volatiles could indicate an artificial rather than natural composition. However, the broader astronomical community has reacted with skepticism and criticism. Multiple experts have described the alien technology hypothesis as unscientific speculation, unsupported by evidence. They argue that all observed characteristics of 3I Atlas can be explained through natural processes, even if some aspects remain poorly understood. The debate reflects deeper tensions in astronomy about how to approach anomalous observations. Conservative scientists prefer to exhaust natural explanations before considering exotic possibilities, while others argue that extraordinary phenomena deserve extraordinary consideration. Regardless of one's position on the alien technology debate, 3I Atlas has succeeded in challenging conventional thinking about interstellar objects and the possibility of detecting artificial constructs in space. The controversy ensures that every future observation of this mysterious visitor will be scrutinized for evidence supporting or refuting the most extraordinary explanation yet proposed. 3I Atlas will make remarkably close approaches to 3 major planets, creating opportunities for detailed observations and raising questions about cosmic coincidences. As 3I Atlas races through our solar system, its trajectory carries it past several planets at distances that astronomical standards consider extremely close. These planetary encounters represent both scientific opportunities and statistical puzzles that have captured the attention of astronomers worldwide. The closest approach will occur with Mars in late October, when 3I Atlas passes within just 12 million miles of the red planet. This distance equals roughly 1/8 of the space between Earth and Mars at their closest approach, placing the interstellar visitor well within the sphere of influence of Martian gravity. The Mars encounter offers unprecedented opportunities for spacecraft-based observations. Multiple robotic missions currently orbiting Mars, including the Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express, will have clear views of 3I Atlas during its approach. These spacecraft carry high-resolution cameras and sophisticated instruments that could reveal details impossible to observe from Earth. The timing proves especially fortuitous because the Mars encounter occurs precisely when Earth-based telescopes lose sight of 3I Atlas behind the Sun. While astronomers on Earth experience observational blackout during the object's most active period, Mars orbiters may provide humanity's only detailed views of this ancient visitor at peak solar heating. Venus represents the second closest planetary encounter, with 3I Atlas passing within 40 million miles of the cloud-shrouded world. This approach distance equals roughly half the typical spacing between Venus and Earth, bringing the interstellar object well within Venus's gravitational sphere of influence. Jupiter presents the final close encounter, with 3I Atlas passing within 22 million miles of the solar system's largest planet. While this distance seems vast compared to the inner planet approaches, it represents an extremely close pass in terms of Jupiter's massive gravitational influence. The statistical probability of these three close encounters occurring by random chance measures less than 0.05%. Such low odds have prompted some researchers to question whether the trajectory represents pure coincidence or something more intentional. From a scientific perspective, the planetary encounters provide valuable opportunities to study how 3I Atlas responds to gravitational perturbations and changing solar illumination. Each close approach will alter the object's path slightly, potentially revealing information about its mass distribution and internal structure. The encounters also offer natural experiments in comparative observation. By viewing 3I Atlas from multiple vantage points throughout the solar system, astronomers can construct three-dimensional models of its shape, rotation, and activity patterns. These remarkable planetary encounters ensure that 3I Atlas will remain under intensive scrutiny throughout its passage, providing unprecedented opportunities to study an interstellar visitor up close. The arrival of 3I Atlas during humanity's technological era raises profound questions about cosmic synchronicity and our place in the universe. When astronomers traced the trajectory of 3I Atlas backward through time and space, they made a startling discovery. This ancient wanderer would have crossed the outer boundaries of our solar system approximately 8,000 years ago, entering the realm of planetary orbits just as human civilization was reaching a critical technological threshold on Earth. 8,000 years ago marked a pivotal moment in human development. Agricultural societies were consolidating into the first cities, written language was emerging in multiple cultures, and complex technologies like metallurgy and astronomy were beginning to flourish. For the first time in Earth's history, an intelligent species was developing the capability to detect and study visitors from other star systems. The timing correlation seems almost too convenient to be coincidental. Of all the moments in Earth's 4.5 billion-year history, 3I Atlas arrives precisely during the brief window when humans possess the technology to recognize its interstellar origin and study its properties. This synchronicity has prompted some researchers to question whether the timing represents pure chance or something more deliberate. Consider the vast scale of cosmic time involved. If 3I Atlas had arrived 100,000 years earlier, it would have passed through our solar system completely unnoticed, its secrets lost forever as early humans struggled with basic survival. If it had arrived 100,000 years later, human civilization might have advanced to interstellar travel, making such visitors routine rather than extraordinary. Instead, 3I Atlas appears at the precise historical moment when humanity first gains the ability to recognize interstellar objects, but remains decades or centuries away from intercepting them. We can observe and study this ancient visitor, but we cannot touch it or sample it directly. The timing creates maximum scientific tantalizing while maintaining ultimate mystery. Some scientists dismiss the timing correlation as meaningless coincidence, arguing that humans naturally notice patterns even in random events. They point out that interstellar objects probably pass through our solar system regularly, and we have only recently developed the technology to detect them. From this perspective, 3I Atlas represents the first in a series of discoveries rather than a uniquely timed event. Others find the synchronicity more troubling, especially when combined with 3I Atlas's unusual characteristics and suspicious planetary encounters. If an advanced extraterrestrial civilization wanted to study humanity without revealing themselves, they might choose precisely this moment in our development to conduct reconnaissance. The timing coincidence adds another layer of mystery to an already enigmatic visitor, ensuring that questions about 3I Atlas extend far beyond simple astronomy into philosophy and speculation about humanity's cosmic significance. Whether coincidence or design, the arrival of 3I Atlas during our technological awakening represents a profound moment in human history. Engineers worldwide have calculated whether humanity could launch a spacecraft to intercept 3I Atlas, revealing the crushing reality of interstellar speeds. Within days of 3I Atlas's discovery, space agencies and research institutions began frantically calculating intercept trajectories. The possibility of sending a robotic probe to humanity's first accessible interstellar visitor represented a once-in-a-lifetime opportunity that might not occur again for decades or centuries. The initial calculations were sobering. 3I Atlas travels so fast that even the most powerful rockets currently available could not match its speed. NASA's Space Launch System, SpaceX's Falcon Heavy, and other heavy-lift vehicles would require multiple gravitational assists and decades of flight time to reach an intercept point. By then, 3I Atlas would have long since departed for the depths of interstellar space. Engineers explored increasingly desperate scenarios. Launching a small CubeSat probe in September or October might allow a high-speed flyby encounter, but the relative velocity would exceed 60 kilometers per second. At such extreme speeds, any imaging attempt would suffer severe motion blur, and the encounter would last only minutes or seconds. The harsh mathematics of orbital mechanics revealed why intercepting interstellar objects presents such extraordinary challenges. Spacecraft designed for solar system exploration typically operate at speeds of 20 to 40 kilometers per second relative to the Sun. 3I Atlas races through our neighborhood at nearly 70 kilometers per second, moving almost twice as fast as our fastest space probes. Even more frustrating, the time constraints make mission planning nearly impossible. Traditional interplanetary missions require years of development, testing, and launch preparation. 3I Atlas offers only months between discovery and departure, compressing normal mission timelines to breaking point. Some researchers proposed radical solutions involving existing spacecraft. The Parker Solar Probe, currently studying the Sun's corona, follows a trajectory that might be modified to approach 3I Atlas. However, the probe's instruments are designed for solar observations rather than detailed object studies, limiting its scientific value. European Space Agency planners examined whether their proposed Comet Interceptor mission could be retargeted toward 3I Atlas. This spacecraft, designed to study pristine comets, could theoretically provide the ideal instruments for interstellar object analysis. Unfortunately, Comet Interceptor will not launch until 2029, years after 3I Atlas departs. The exercise in mission planning highlighted humanity's current limitations in deep space exploration. While we can detect and study interstellar visitors from afar, we remain largely powerless to intercept them for detailed analysis. 3I Atlas serves as a humbling reminder of how much our spacecraft technologies lag behind the speeds required for interstellar encounters. Future missions may benefit from lessons learned during the 3I Atlas opportunity, developing rapid response capabilities and high-speed intercept technologies for the next interstellar visitor. 3I Atlas belongs to an ancient stellar community that witnessed the violent birth pangs of our galaxy, carrying secrets from cosmic prehistory. The thick disk of the Milky Way represents one of the galaxy's oldest and most exotic neighborhoods, populated by stars that formed during an era of cosmic chaos billions of years before our Sun existed. 3I Atlas's motion through space reveals its membership in this ancient stellar population, making it a messenger from the galaxy's turbulent youth. Unlike the orderly thin disk where most familiar stars reside, the thick disk formed during a period of galactic violence when massive collisions and gravitational disruptions dominated the cosmic landscape. Dwarf galaxies crashed into the growing Milky Way, their stars and planetary systems scattered into highly elliptical orbits that carry them far above and below the main galactic plane. Stars in the thick disk population move differently than their thin disk cousins. While our Sun follows a nearly circular orbit around the galactic center, thick disk stars trace elongated paths that plunge through the galactic plane and soar into the sparsely populated halo regions. These extreme orbits result from the gravitational chaos that characterize the galaxy's assembly process. The chemical composition of thick disk objects also differs dramatically from solar system materials. These ancient stars formed from gas clouds depleted in heavy elements, containing much lower concentrations of metals forged in previous generations of stellar explosions. Objects forming around thick disk stars would reflect this primitive chemistry, potentially explaining some of 3I Atlas's unusual spectral characteristics. The thick disk environment proves especially hostile to planetary systems and their associated comets and asteroids. The extreme stellar orbits carry these systems through regions of varying star density, subjecting them to frequent gravitational perturbations from passing stars and molecular clouds. Such encounters can easily disrupt outer planetary systems, ejecting comets and asteroids into interstellar space. This ejection process may explain why thick disk populations produce disproportionately large numbers of wandering objects like 3I Atlas, while thin disk systems like our own maintain relatively stable configurations for billions of years. Thick disk systems experience constant gravitational harassment that strips away their outer components. The thick disk origin also provides insights into 3I Atlas's extreme age. Stars in this population typically formed 7 to 10 billion years ago, making them among the oldest objects in our galactic neighborhood. Comets ejected from such ancient systems would carry material that predates our solar system by billions of years. 3I Atlas serves as an archaeological specimen from this ancient stellar community, offering humanity its first opportunity to study matter from the galaxy's primordial era. Its composition and structure may reveal conditions that existed when the Milky Way was young and chaotic, billions of years before Earth formed. The thick disk heritage of 3I Atlas transforms this visitor from a simple interstellar comet into a cosmic time capsule from the galaxy's violent birth. The mysterious absence of expected chemical signatures from 3I Atlas challenges fundamental assumptions about comet composition and behavior. When astronomers first confirmed that 3I Atlas was indeed a comet rather than an asteroid, they immediately began searching for the characteristic spectral lines that reveal a comet's chemical composition. Every active comet produces distinctive emissions as solar heating vaporizes its surface materials, creating a unique fingerprint of gases that escape into space. But 3I Atlas remained stubbornly silent across most of the electromagnetic spectrum. Detailed spectroscopic observations from multiple observatories failed to detect the bright emission lines of water vapor, carbon monoxide, carbon dioxide, and other molecules that typically characterize active comets. The absence of these expected signatures created a puzzle that continues to baffle researchers. Water vapor represents the most glaring omission from 3I Atlas's spectrum. Virtually every comet studied by astronomers shows strong water emission lines when solar heating begins sublimating surface ice. Water makes up the primary component of most cometary nuclei, and its spectral signature serves as the defining characteristic that distinguishes comets from asteroids. The lack of water signatures could indicate several possibilities, none of them conventional. 3I Atlas might have lost most of its water ice during billions of years in interstellar space, leaving behind a dehydrated remnant composed primarily of rocky material and complex organic compounds. Alternatively, its water might remain locked beneath a protective crust that prevents normal sublimation. Carbon-bearing molecules also remain mysteriously absent from the spectrum. Most comets show clear evidence of carbon monoxide, carbon dioxide, and various organic compounds when they approach the sun. These molecules provide crucial information about conditions in the original planetary system where the comet formed. Their absence from 3I Atlas suggests either unusual formation conditions or extreme processing during its interstellar journey. Some astronomers propose that 3I Atlas represents a transition object between comets and asteroids. containing just enough volatile material to create the faint coma observed in images, but not enough to produce detectable spectral emissions. This would make it fundamentally different from both typical comets and asteroids. Another possibility involves the object's extreme speed through the solar system. While conventional comets spend months gradually warming as they approach the Sun, 3I Atlas races through temperature zones so quickly that normal sublimation processes might not have time to develop. The rapid motion could suppress typical outgassing, explaining both the faint coma and absent spectral lines. The spectral silence of 3I Atlas forces astronomers to question basic assumptions about comet behavior and composition. This ancient visitor follows none of the rules established by solar system comets, suggesting that interstellar objects may represent entirely different categories of cosmic debris. Until 3I Atlas begins showing expected spectral signatures or provides alternative explanations for their absence, it will remain one of the most enigmatic objects ever studied. Computer simulations tracing the path of 3I Atlas backward through time reveal a journey that spans millions of years and thousands of light years through the galaxy. Advanced orbital mechanics calculations have reconstructed the probable route that 3I Atlas followed during its epic journey from the thick disk of the galaxy to our solar system. These simulations represent some of the most complex astronomical computations ever attempted, tracking a single object's motion through the changing gravitational landscape of the Milky Way over cosmic timescales. The analysis begins with 3I Atlas's current position and velocity, then integrates its motion backward through time, while accounting for the gravitational influences of every major stellar component in our galactic neighborhood. The calculations must consider not only the smooth gravitational field of the galaxy's dark matter halo, but also the discrete gravitational effects of individual stars, star clusters, and molecular clouds encountered along the way. Tracing the object's path reveals that 3I Atlas followed a highly elliptical orbit around the galactic center, spending most of its time in the sparsely populated regions above and below the main stellar disk. This orbital pattern matches the thick disk population, confirming the object's ancient heritage and exotic origin. The simulations suggest 3I Atlas may have wandered through interstellar space for hundreds of millions of years before stumbling into our solar system. During this vast journey, it would have passed through diverse galactic environments, from the dense star-forming regions near the galactic center to the empty voids of the outer halo. Gravitational encounters with passing stars would have gradually altered 3I Atlas's trajectory over time, creating the complex orbital history revealed by the computer models. Each stellar encounter imparted tiny velocity changes that accumulated over millions of years, eventually directing the object toward our solar neighborhood. The trajectory analysis also reveals several potential source regions where 3I Atlas might have originated. The most likely candidates are ancient planetary systems in the thick disk that suffered gravitational disruption billions of years ago. Passing stars or molecular clouds could have ejected 3I Atlas from its birth system, sending it on the long journey that eventually brought it to our attention. Remarkably, the simulations show that slight changes in 3I Atlas's initial velocity would have sent it on completely different paths through the galaxy. A velocity difference of just a few kilometers per second could have caused the object to miss our solar system entirely, passing harmlessly through interstellar space without ever being detected. The precision required for 3I Atlas to arrive at precisely the right time and place to be discovered by human astronomers seems almost impossibly small. This fine-tuning has prompted some researchers to question whether the object's trajectory represents pure chance or some form of guidance. The trajectory analysis provides a roadmap of 3I Atlas's cosmic odyssey, revealing the vast scales of space and time involved in interstellar travel. 3I Atlas shines far brighter than any natural object of its apparent size should, creating a photometric puzzle that challenges our understanding of interstellar materials. When astronomers first measured the reflected sunlight from 3I Atlas, the brightness readings seemed impossible. For an object at its distance from the Sun, the amount of light detected suggested either an enormous size or an extraordinarily reflective surface. Neither explanation fits comfortably with conventional models of interstellar objects. If 3I Atlas truly measures 15 to 20 kilometers across, as early estimates suggested, it would represent by far the largest interstellar object ever discovered. The statistical probability of detecting such a massive wanderer remains vanishingly small, making this size estimate highly suspect among the astronomical community. Alternatively, the brightness could result from an unusually high albedo, meaning 3I Atlas reflects much more sunlight than typical space rocks. Most asteroids and comet nuclei reflect only 3 to 5% of incoming sunlight, appearing quite dark when viewed from space. 3I Atlas would need an albedo approaching 20 to 30% to explain its observed brightness at a more reasonable size. Such high reflectivity suggests surface compositions very different from familiar solar system objects. Fresh ice surfaces can achieve high albedos, but 3I Atlas shows little evidence of extensive water ice sublimation. Complex organic compounds formed during billions of years in interstellar space might create unusual reflective properties, though laboratory studies of such materials remain limited. The brightness anomaly deepened as 3I Atlas approached the Sun and gradually increased in apparent magnitude. Most comets brighten rapidly, as solar heating vaporizes increasing amounts of surface material, creating expanding comas that reflect more sunlight. But 3I Atlas brightened more slowly than expected, following a curve that suggests minimal increase in active surface area. This shallow brightening pattern indicates that 3I Atlas responds differently to solar heating than conventional comets. Either its surface materials resist normal sublimation processes, or the object maintains such high reflectivity that additional outgassing produces little noticeable change in brightness. Infrared observations added another layer to the brightness puzzle. 3I Atlas appears warmer than expected for its distance from the Sun, suggesting either unusual thermal properties or some form of internal heat generation. The thermal excess could indicate subsurface materials with different thermal conductivity than typical cometary ice and rock. Polarization measurements provide additional clues about 3I Atlas's surface properties. The way reflected sunlight becomes polarized depends on the size, shape, and composition of surface particles. Preliminary polarization data suggest 3I Atlas has surface characteristics, unlike any previously studied solar system object. The brightness anomaly forces astronomers to reconsider fundamental assumptions about interstellar material properties. 3I Atlas behaves photometrically like no known category of solar system object, suggesting that billion-year journeys through interstellar space create surface conditions unlike anything in our local neighborhood. Until detailed spectroscopic analysis reveals the true composition of 3I Atlas, its brightness will remain one of the most perplexing aspects of this mysterious visitor. After weeks hidden behind the Sun during its most active period, 3I Atlas will emerge in late November as a transformed object displaying its full cometary glory. The cosmic hide-and-seek game of 3I Atlas reaches its dramatic conclusion in late November 2025, when the ancient visitor finally emerges from behind the Sun and becomes visible to Earth-based telescopes once again. This reappearance represents one of the most anticipated events in modern astronomy, as scientists prepare to witness how solar heating has transformed their enigmatic guest. During its hidden passage through perihelion in late October, 3I Atlas experienced the most intense solar radiation of its billion-year journey. Surface temperatures likely reached hundreds of degrees, potentially vaporizing subsurface materials that remained frozen throughout the object's epic voyage through interstellar space. This thermal shock may have cracked protective crusts and exposed fresh materials to space. Astronomers expect the reappearing 3I Atlas to display dramatically enhanced cometary activity. The faint, barely detectable coma observed during its inbound approach should have expanded into a prominent envelope of gas and dust, extending thousands of miles from the nucleus. Solar-wind interactions may have shaped this expanding material into the classic curved tail that makes comets among the most spectacular objects in the solar system. The November emergence occurs in the pre-dawn sky, where 3I Atlas will appear as a morning object visible before sunrise. Unlike its earlier apparition high in the evening sky, the reappearing comet will be positioned near Venus, creating photogenic opportunities for both professional astronomers and amateur observers equipped with modest telescopes. Spectroscopic analysis of the post-perihelion 3I Atlas promises to reveal chemical signatures that remained hidden during its approach phase. The intense solar heating may have sublimated water, ice, carbon compounds, and other volatile materials that will finally provide definitive information about the object's composition and origin. These emissions could resolve questions about whether 3I Atlas truly represents ancient cometary material or something more exotic. The timing of the reappearance also allows comparison with pre-perihelion observations to assess how much material 3I Atlas lost during its closest solar approach. Changes in brightness, coma size, and spectral characteristics will reveal how this interstellar visitor responds to the sun's influence compared to conventional comets. Ground-based telescopes will not be the only instruments tracking the re-emergent 3I Atlas. Space-based observatories, including Hubble and James Webb, will continue their intensive monitoring, potentially revealing details about the object's internal structure and composition impossible to detect from Earth. The November reappearance marks the beginning of the final observational phase for 3I Atlas. As the object races away from the Sun toward the outer solar system, it will gradually fade and cool, eventually becoming too dim for detailed study. Astronomers have perhaps 6 months to extract maximum scientific value from this ancient messenger before it disappears into interstellar space forever. The transformed 3I Atlas emerging from solar conjunction may finally answer the fundamental question of whether this visitor represents a conventional interstellar comet or something far more extraordinary. 3I Atlas heralds a new era of cosmic archaeology, as next-generation telescopes prepare to discover thousands of interstellar visitors hidden in the darkness. The detection of 3I Atlas represents more than just the discovery of another exotic cosmic visitor. It marks the beginning of a revolutionary period in astronomy, when interstellar objects transition from rare curiosities to routine discoveries, fundamentally changing our understanding of the galaxy's hidden population of wandering worlds. The key to this transformation lies in the Vera C. Rubin Observatory, currently preparing for first light operations in Chile. This revolutionary facility features the largest digital camera ever constructed, capable of surveying the entire visible sky every few nights with unprecedented sensitivity. When fully operational, Rubin Observatory will detect moving objects millions of times fainter than 3I Atlas, revealing a vast population of interstellar visitors previously invisible to human instruments. Preliminary estimates suggest Rubin Observatory might discover one new interstellar object every month once it reaches full operational capacity. Over its planned 10-year survey, the facility could catalog several thousand visitors from other star systems, creating the first comprehensive census of interstellar objects in our galactic neighborhood. This flood of discoveries will revolutionize our understanding of planetary system formation and evolution throughout the galaxy. Each interstellar visitor carries chemical and physical information about its birth environment, potentially revealing the compositions and characteristics of planetary systems around stars that died billions of years ago. The diversity revealed by just 3 interstellar objects suggests that upcoming discoveries will challenge every theoretical model of planetary system architecture. From Oumuamua's mysterious acceleration to Borisov's familiar cometary behavior to 3I Atlas's ancient origins, each visitor has broken established patterns and forced scientists to expand their conceptual framework. Future interstellar object discoveries will also provide unprecedented opportunities for detailed study. Unlike 3I Atlas, which was detected only months before its closest solar approach, Rubin Observatory will identify many visitors years before perihelion. This extended lead time will allow careful mission planning for spacecraft intercepts, potentially enabling humanity's first direct sampling of materials from other star systems. The technological capabilities required for interstellar object science are advancing rapidly. Artificial intelligence systems are being developed to automatically identify and track fast-moving objects in telescope data streams, ensuring that no potential visitors escape detection. Rapid response telescopes will provide immediate follow-up observations of newly discovered objects, characterizing their properties before they fade from view. International cooperation in interstellar object research is also expanding, with space agencies worldwide developing protocols for coordinated observations and potential intercept missions. The scientific value of these cosmic messengers has created unprecedented collaboration between traditionally competitive national space programs. 3I Atlas serves as a preview of the cosmic archaeology revolution that awaits. Soon, interstellar visitors will transform from headline-making discoveries to research tools for studying the galaxy's vast inventory of planetary systems, both living and dead. The age of interstellar object science has only just begun. 3I Atlas will leave behind a permanent transformation in how humanity understands planetary systems, galactic evolution, and our place in the cosmic community. The scientific impact of 3I Atlas extends far beyond the specific measurements and observations gathered during its brief passage through our solar system. This ancient visitor has fundamentally altered our perspective on planetary system architecture, galactic chemical evolution, and the processes that shape cosmic environments throughout the Milky Way. Perhaps most significantly, 3I Atlas has demonstrated that interstellar space contains a vast population of objects ejected from planetary systems throughout galactic history. These wandering remnants preserve chemical and physical information about stellar environments that existed billions of years ago, creating an accessible library of galactic archaeology that scientists are only beginning to explore. The extreme age of 3I Atlas, potentially predating our solar system by billions of years, provides the first tangible connection to planetary formation processes in the early galaxy. Its composition and structure offer insights into how planets and smaller bodies formed around ancient, metal-poor stars very different from our Sun. This information helps astronomers understand how planetary system characteristics have evolved as the galaxy matured and became enriched with heavy elements. The size and brightness anomalies associated with 3I Atlas have forced a complete reevaluation of interstellar object statistics and formation mechanisms. The discovery that such large objects can survive billion-year journeys through interstellar space challenges models of how cosmic debris disperses and degrades over time. 3I Atlas has also revealed the importance of advanced surface processing during interstellar transit. The radiation chemistry that occurs over cosmic timescales creates material properties unlike anything found in our solar system, suggesting that interstellar objects represent entirely new categories of cosmic matter, worthy of detailed study. The trajectory analysis and thick disk origin of 3I Atlas provide crucial data about galactic dynamics and stellar population mixing. By studying how objects move between different galactic environments, astronomers gain insights into the large-scale processes that have shaped the Milky Way's structure and evolution over billions of years. From a technological perspective, 3I Atlas has highlighted both the capabilities and limitations of current astronomical instrumentation. The successful detection and characterization of this visitor demonstrate the power of modern sky surveys and rapid response telescope networks. However, the inability to intercept or sample the object directly has motivated development of new spacecraft technologies for future interstellar visitor encounters. The international coordination required to study 3I Atlas has also created new models for collaborative astronomy that will benefit future research efforts. The successful mobilization of telescopes worldwide demonstrates how the astronomical community can respond rapidly to unexpected discoveries. Perhaps most importantly, 3I Atlas has expanded human imagination about the diversity and abundance of objects drifting through our galaxy. This ancient messenger reminds us that space between the stars is not empty void, but rather a vast repository of cosmic history waiting to be explored. The legacy of 3I Atlas will endure long after the object itself fades into the darkness beyond our solar system. 3I Atlas delivers a profound message about cosmic time, galactic citizenship, and humanity's emerging role as witnesses to the universe's ancient history. As 3I Atlas completes its brief visit to our solar system and prepares to resume its eternal journey through interstellar space, this ancient wanderer leaves behind more than scientific data and astronomical measurements. It carries a cosmic message about time, distance, and the interconnected nature of all matter in our galaxy. The message begins with humility. 3I Atlas reminds us that our solar system represents just one small corner of a vast galactic community that has existed for billions of years before Earth formed. The heavy elements in our bodies, forged in stellar furnaces and dispersed by cosmic explosions, share common origins with the materials that compose this interstellar visitor. We are, quite literally, made of star stuff that has wandered the galaxy for eons. 3I Atlas also speaks to the incredible patience required for cosmic processes. Its billion-year journey through interstellar space spans a timeline almost incomprehensible to human experience. Yet this vast duration represents merely a brief moment in galactic history, during which countless other objects have followed similar paths between the stars. The universe operates on scales that dwarf human civilization, yet we have developed the intellectual tools to recognize and study these cosmic processes. The visitor carries a message about diversity and surprise. Despite decades of studying solar system objects, 3I Atlas has confounded every prediction and challenged every theoretical model. Its unusual characteristics remind us that the universe contains phenomena far beyond our current understanding, ensuring that cosmic exploration will continue revealing surprises for generations to come. Perhaps most significantly, 3I Atlas delivers a message about emergence and capability. For the first time in Earth's history, a technological species has developed the ability to recognize visitors from other star systems and extract meaningful information about their origins and properties. Humanity has crossed a threshold, joining the ranks of hypothetical civilizations capable of studying galactic processes directly. This emergence carries responsibility as well as opportunity. As cosmic awareness expands, humans become stewards not just of Earth's environment, but of knowledge about galactic processes and interstellar phenomena. The information gathered from 3I Atlas and future visitors will inform decisions about humanity's eventual expansion beyond our solar system. The timing of 3I Atlas's arrival during humanity's technological adolescence seems remarkably convenient, arriving precisely when we can recognize its significance but before we become capable of routine interstellar travel. This coincidence raises profound questions about cosmic synchronicity and the possibility that intelligence naturally emerges during specific phases of galactic evolution. As 3I Atlas departs our neighborhood forever, it carries with it the reflected photons of human civilization. Radio and light emissions from Earth have interacted with this ancient visitor, creating a tenuous connection between our young technological society and a cosmic wanderer older than our world. The cosmic message of 3I Atlas resonates across scales from the personal to the universal. We are participants in galactic processes that connect all matter across space and time. This ancient messenger has made us citizens of the galaxy, responsible for preserving and extending the cosmic story of which we are all part. In the darkness beyond our solar system, 3I Atlas continues its eternal journey, carrying with it the faint traces of its encounter with humanity's first generation of cosmic archaeologists.